So the goal of this lecture is to give an overview of the proof of security of the BB84 protocol for quantum key distribution. And all the ingredients for this proof of security have already been put in place. What we're going to need is the purified form of the BB84 protocol. We're going to use the results on privacy amplification that we've seen, and we're going to use results on the guessing game that we saw a couple weeks ago. So let's get started. Remember the BB84 protocol. I'm not giving you the whole protocol again. Remember the purified form of the protocol, where in the first step, Eve got to prepare an arbitrary state, Rho A B E, of which she kept system E, distributed the n qubits that comprised system A to Alice, and the n qubits that comprised system B to Bob. In this way, establishing some form of tripartite entanglement between Eve, Alice, and Bob. And then the whole protocol runs, so Alice and Bob make their choice of bases, their measurements, they check that the outcomes agree, and then they perform the steps of information reconciliation and privacy amplification. Now, we've already seen previously that this protocol is correct, meaning that if Eve prepares the state that we are hoping that she prepares, a state which is simply n copies of the EPR pair phi plus shared between Alice and Bob and nothing on her side, then the protocol is going to be correct, meaning that at the end of the protocol, Alice and Bob will come up with the same shared key K, and this key will be uncorrelated with the eavesdropper. Correctness is okay. What we want to do is prove security or secrecy, and if you remember the criterion for epsilon secrecy of a quantum key distribution protocol, what's required is that the joint state of the key and the eavesdropper's side information should be indistinguishable, as measured by the trace distance, from a state that's totally uniform on the key register and uncorrelated from the adversary's or the eavesdropper's side information Rho E. So that's our goal. And we've already made one important step towards achieving this goal. This is achieved by the task of privacy amplification, which told us that in order to achieve epsilon secrecy, it's in fact sufficient to obtain a weaker criterion, which is that the mean entropy of Alice's raw key bits before the key is obtained, conditioned on the eavesdropper's side information E, is at least some amount. So what is this XAR here? Remember that in the protocol, Alice makes measurements. She obtains a string XA. XA is the bits that are not discarded, so ones that correspond to the same choice of basis for Alice and Bob. And then this string of outcomes is split into two. There's the bits that are tested, XAT and XBT, and the bits that are kept in order to get the key. And these are the raw key bits, XAR and XBR. So these are the bits that are used in order to perform information reconciliation and privacy amplification. These bits are tested. And now what privacy amplification achieves is that as long as the mean entropy of the bits that are used for the task is large enough, then we know that we can obtain a secure key simply, for instance, by applying a quantum proof extractor based on two-universal hashing that we saw last week. So this is what we have to show. How are we going to argue it? Well, let me do it for you on making some simplifying assumptions. Let me assume, even though this is not possible, that the bits used for the raw key are in fact the same as the bits that are used for the testing. It's not possible because these bits are revealed in the public communication channel, so Eve in fact has access to those bits. But let's just, put that fact aside and imagine that XAR is equal to XAT. And let's also make the simplifying assumption that the test passes perfectly. There's no error at all. All bits are in agreement. So Alice and Bob observe that the string XAT is equal to the string XBT. In that case, what is the probability that Eve guesses the string XAT? This is the probability that XAT is equal to XBT, because I assumed that the test passes, so this is in fact always the case, is equal to some guess XE that Eve makes based on the bases that she learned about and her side information E. What is this expression? Here you should recognize something. It's exactly the probability that A, B, and E succeed in the tripartite guessing game that you saw in week 2. And this we bounded. We saw that this is always going to be at most a half plus 1 by times root 2, the number of rounds, which in this case is n. And this is approximately equal to 2 to the 0 minus 0.23 n, if you do the calculation. So there we are, under these two simplifying assumptions that the rounds used for the raw key and the rounds used for the testing are the same, and that the tests pass with certainty, so we observe perfect agreement, then security for BB84 via privacy amplification is reduced to showing that the success probability of A, B, and E in the tripartite guessing game is as small as possible, which is something that we've already seen. And that establishes security. Of course, there is still these two simplifying assumptions. In practice, we know that these are not going to hold. Alice chooses some rounds to test. These are the set T, and we're going to observe some error rate delta that Alice will observe, delta A and delta B. In that case, you get a slightly weaker result. What you can show is that the guessing probability is going to be equal to 2 to the minus kappa times kappa prime times r, where kappa prime is similar to what we had before, but a little bit weaker, so it's approximately equal to kappa we had before. This was equal to 0.23, roughly, minus, and there's a little bit of a loss that's going to look like the binary entropy function applied to this error rate, delta A. And you can learn more about how this is proved in the lecture notes. So that wraps up the analysis of the BB84 protocol, at least making, some assumptions. So next week and the week after, we're going to see a stronger proof of security of the protocol that's called the device-independent proof of security that's going to make even less assumptions about what Alice and Bob know in this protocol. Is going to give more power to the eavesdropper. And we'll see this in a little bit more detail.